Hi, my name is Indu Panigrahi, and I'm part of the RIS 2022 cohort. In this talk, I will describe the project I did this summer, which was detecting hazardous conditions along bus routes. Hazardous conditions such as snow-covered sidewalks limit the safety and accessibility of public transit. We specifically look at detecting snow-covered sidewalks along bus routes on which pedestrians could slip when walking to bus stops. Our goal is to generate an alert if the bus encounters a snow-covered sidewalk. Smart city infrastructures aim to facilitate this task among many others through the use of computer vision. However, most state-of-the-art deep learning models train on datasets containing thousands of images, which we do not have since hazardous conditions are generally rare. Furthermore, it would be difficult to train a model to look at a snowy image and be confident that a sidewalk exists under the snow. Some geometry-based and self-supervised methods have been developed to address a similar problem of detecting roads in adverse weather conditions. These methods do well when the road is partially occluded, as in night settings or fog, but not when fully obscured by snow. We use images taken on a bus that travels around Pittsburgh and Washington County in Pennsylvania as data. However, instead of annotating the data, we take advantage of the fact that the bus regularly runs along a set route to learn the locations of the sidewalks. To demonstrate our method on one stretch of road, we first take images from 2 to 3 runs of the same stretch in clear weather and use a structure from motion pipeline called ColMap to render a 3D point cloud representation of the scene. We then estimate the ground plane and project the masks of the sidewalks obtained from the mask-to-former model onto the ground plane, and we save the projected points. You can think of all these steps as essentially saving a 3D model of the sidewalks. Then, on a future snowy run, we use the GPS information that comes with the images to identify the images that belong to that stretch. Since GPS is not very precise, we further localize an image by rerunning ColMap with the image added. Using the generated camera extrinsics for that image, we project the saved sidewalk points into the image and compare the percent of the sidewalk that is covered by the snow in the image to an alert threshold. If the coverage is greater than the threshold, we generate an alert. These steps compare the snow coverage to the expected sidewalk locations by using the saved 3D model. Here is an example result where the blue pixels are snow and the yellow pixels are the saved sidewalk points that are projected into this image. For a quantitative evaluation, we check the percent of manually selected images from our route that are correctly classified at incremented thresholds, so higher is better. In particular, the test images are split into 3 categories. First, we evaluate on images from a new clear weather run. This trivially does well at all thresholds because there is no snow present in the images. Next, we evaluate on images from a snowy run where the sidewalks are covered with snow. Our method does well up until around a threshold of 0.7. Lastly, we evaluate on images from a snowy run where the sidewalks have been cleared. This category is particularly important because there is snow present in the image, but it's not on the sidewalk. As we increase the threshold, the performance improves. Since we need a threshold that performs well in both these situations, we identify somewhere around 0.6 as a reasonable threshold in this case. In conclusion, we present a less data-intensive method that we demonstrate for detecting snow-covered sidewalks on bus routes. However, our method can also generalize to other conditions, such as snow-covered bike lanes. Future work could include, firstly, optimizing ColMap since it currently takes about 20 minutes to run per reconstruction, and secondly, generalizing to rural areas where there may not be as many salient key points for ColMap to latch onto. I would like to thank my mentor, Dr. Christoph Mertz, for advising this project and providing feedback throughout the summer. I would also like to thank Tom Boo for providing additional support and resources. And finally, I would like to thank Dr. John M. Dolan, Rachel Burson, the RIS program, and sponsors for organizing and supporting this research experience. Thank you for listening.